All right, very good. Well, so we've been doing these videos, more of them lately, talking with all of our new fellow partners and Telos team members. So today we've got a very special guest. I'll let him introduce himself. But wonderful to have you here, Milos. Maybe you could tell us a little bit about yourself, your background, and what you're up to these days.
Thanks, John. Thanks for the introduction, and thanks for having me here. I'm coming from, so my name is Milos Stanisavljevic. I'm CTO of Ponos Technology. And I'm coming from the background of like engineering, so like electrical engineering, with a bit of software engineering. And I've been like for quite some time basically in different technologies that involve mainly like hardware design, but also like software hardware co-design, which is becoming in recent years like a very prominent term. I originally come from Serbia, where I did my undergrads and my masters at University in Belgrade in electrical engineering. Moved like almost 20 years ago to Switzerland. Did my PhD there at University in Lausanne in Federal Technical School, and I did it like in the field of microelectronics. Worked in different companies before joining IBM maybe 12, 13 years ago. And I work there on a lot of like it's a research lab in Zurich. I work on a lot of cutting edge technologies, including like signal processing, even some blockchain stuff in its early days. It's been like more than like 8 years since then, since IBM had and still has particularly the lab in Zurich where I worked, a very good group on blockchain. And this is probably where I first time caught the bug of like crypto technologies. And the next my kind of I mean in parallel kind of to these, I was a lot involved in like crypto, but more as like cryptographic engineering stuff, making basically hardware that is like crypto resistance for encryption, decryption, and so on. And also I'm kind of a lot still in signal processing, which kind of is kind of an important branch that is like more and more involved these days in blockchain, particularly in like ZK technologies, zero knowledge based technologies. And it all started probably it's already 3 years ago. Time flies. Maybe even more than three and a half years ago, when Slobodan first time introduced me to an idea to kind of make a company. Because at that time already, like he had this kind of visionary idea that like, okay, ZK is coming, and it's a new technology that is very much computing intensive. And today we are doing this like using mainly CPUs, like general purpose computing, but or high performance computing, but we'll really need a specialized kind of hardware and technology for this in the future. And this is not the first time we've seen this with kind of Bitcoin mining, where it first started like on general purpose CPU, migrated very quickly to GPUs, and then to like this particularly FPGA kind of based specialized miners, and then moved to ASIC, and this is how it's done for the previous almost 10 years exclusively in ASICs. And this is probably the trend, almost certainly the trend that will follow also with like ZK technologies and future of blockchain. And this I immediately recognized this as kind of a very good idea, and saw the potential in things that are coming, and like jumped the ship at that time. And yeah, since then, yeah, it's been a while. We are in this kind of together, and it's been one of a hell of a journey, and a very very interesting one. And yeah, we really looking forward to what this technology can bring us.
Yeah, wonderful. Well, so for our audience, I think given you're the CTO of Ponos Technology, I think we can have a little bit more of a technical talk here, because I'd love to hear your thoughts. But maybe before we dive into that, and we can talk more about ZK proving, and some of the details around that, particularly around the proving markets as well, signal processing. But you mentioned you're from Belgrade, and we just had before we get there, we just had Belgrade, and of course Telos was a sponsor there. I was a sponsor there. We had a great time. I'd be very curious because one of the things that I'm noticing, particularly throughout the entire Balkan region, but definitely also in Belgrade. First of all, I know you as someone with tremendous work ethic. I know you work very, very hard. I know you're very committed, and you're also technically very sharp. And it seems to me like Belgrade now somehow is a hub for tremendous Web3 activity. Very, very strong young people who are in particular quite technical. And so I'm just wondering, maybe you could talk a little bit about Belgrade as you know it, maybe some of the things that you're seeing, and why it is that this ecosystem seems to be flourishing, in this place of all places.
Of course. Yeah, it's great you mentioned it, and yeah, the conference in Belgrade was very nice, and it's also, I would like to thank you for promoting in this way basically Belgrade, and promoting the blockchain industry there. People know a lot. I mean, I see this as kind of like two kind of routes. First one, I think, is that it has in general Belgrade and Serbia. I mean, also like Novi Sad and so on. Very strong like engineering culture. A lot of very very good engineers, software developers, tech savvy people, and this is extremely high percentage compared to total amount of university graduates, undergrads, and so on. People that go into technology, particular into kind of IT and in general like engineering, and they're very much into new stuff, new technologies. You can see this kind of everywhere. So many companies on cutting edge technologies, AI, blockchain, these days are having their research centers, development centers, and so on in Belgrade. That's kind of one part of the story. Another part of the story, I think, from the very beginning, in general in Serbia, in Belgrade, people were very much open into cryptocurrencies. I would say more than what's kind of average, and you can say that's kind of still there is some sentiment in general, particularly in in the Western countries, in the developed world, of being skeptical about the blockchain technologies, about the cryptocurrency world, and so on. And I think because there is kind of a period from maybe 30 years ago when there was a very, very rough transition period in the Balkans, particularly in the former Yugoslavia, in Serbia. And people went to kind of poverty, but also struggled with the currency, with the national currency, with exchanging these and so on. And got, I think from there, were more open into kind of experimenting with kind of new forms of payment systems, currency type of investment, and so on. And this is why, already from the early days, a lot of people were into kind of cryptocurrencies, in the crypto mining, and so on. With this, they were kind of the early adopters and got to know the technology. So and I think today, like on average, the knowledge in particularly understanding of blockchain in general population is much higher. What I can see, for example, in Belgrade, in Serbia, than what is the case in Switzerland. Even though like Switzerland, where I'm based now for 20 years, is kind of calls themselves as kind of a crypto valley of Europe and so on. And it is friendly towards blockchain technologies, but people don't know what it is and don't have this kind of understanding and also enthusiasm about this. So I think these are the two kind of primary things. And when you put these two together, it's like engineers and developers which have substantial technical knowledge on one hand, and on the other hand they have enthusiasm for like blockchain technologies. Yeah, you get exactly what you have today, like a very a lot of kind of development and successful like companies, a lot of people working there, and a lot of talent.
Yeah. Yeah, it's interesting you mentioned that. My family background's from Yugoslavia as well. My father was an engineer. He was an aerospace engineer. And, when you look at a place like Yugoslavia, for many decades, it was basically subsidized by cheap energy from the Soviet Union. And actually, it didn't really have a free market economy. It was sort of in the middle, maybe, but not really. Yet it still had, for example, its own aerospace industry. And so I remember when things started to deteriorate, or it was clear that it was starting to deteriorate, for example, in the early mid-'80s, so many aerospace engineers migrated to Canada and the U.S., and my father ended up working at Boeing for many years, and I grew up in Seattle, and it was like full of Serbs and other Yugoslav engineers, and that was kind of like there was a huge contingent of them that worked on the 777 extended range cargo aircraft, for example, and so on. So, and then also there's a very famous, it's on the internet, on crypto Twitter, everything, the Zimbabwe, I think $100 billion note. But actually in 1992, in what was left of Yugoslavia at the time, there was like 100 million and there was even like a billion.
We had a 500 billion note, I think, and that was
exactly
still probably the largest one ever.
And that's Europe. That's Europe in 1992. And so that leaves this impression on the young people who are transitioning into a free market, Western-oriented society, and somehow crypto is native to them insofar as they understand that maybe sometimes government policy around monetary science is not really the best way to go. Okay, so maybe diving a little bit more into some of the technical stuff around ZK. So oftentimes we talk about it, and I've talked about it many times. So let me start with your definition of ZK, and not and obviously revealing something, revealing the content. I don't mean high level. I mean, what does it mean to you in sort of a precise, very succinct way? And then maybe after that, you can kind of talk a little bit about how you see this evolving, particularly around the proving markets that we think are to come.
Mm-hmm. So like from one point, one can think, of course, in kind of a way of traditional definition, which to kind of people who are not into this looks a little bit like magic, because on one hand you have all the information. You can prove that you have all the right information without revealing absolutely anything. I mean, people technically see this, okay, there is some very complicated maths involved. They can perceive how this works, but what is kind of harder to grasp is like how this can be applied and why this is important. And like there are always like these kind of basic examples. However, I think it's important like to see the bigger picture and kind of the benefit of ZK technologies in the context of blockchain in particular, and how blockchain technologies should develop. And of course, the first thing that comes to mind, and everybody's kind of on board with that and agree with this, is kind of making things anonymous. So like enabling intrinsically anonymity, which kind of is an important, and I think everybody is kind of in general population is concerned for the privacy these days, and also importance of like privacy and transactions. This is something that probably is a misconception. People think that in traditional like blockchain there is anonymity. Yes, there is anonymity, but there is no like anonymity in terms of who owns the account, from where to where transaction goes. But there is no anonymity in like which transactions, how much are the transactions, and so on one hand. On the other hand, like whenever there is a contact point between like the cryptocurrency and the fiat currencies, you can I mean, this anonymity is not anymore there, and I mean it's kind of discovered. And I think one important point, of course, is that implicitly, so the transactions and everything that is going on the blockchain is kind of hidden under this shield of zero knowledge. But even more so, like going into more kind of technical aspects, the thing that really enables, and we see this in IT in general, I think the main thing is kind of scalability. And if you see the problems of blockchain technologies, and we are seeing this as maybe not like imminently now, but it's going to come when we witnessed this, like for example during the bull markets, when particularly like a lot of mining was involved with Ethereum, when the price of transactions like went really high, when more transactions were involved and so on, simply because the system was not able to handle and to scale with such a kind of increase in demand. And I mean, up to certain points, scalability can be resolved in a traditional way, but really, what kind of is a holy grail for this is zero knowledge technology, because this is where you are able to take hundreds of transactions, if not thousands, a bunch of smart contracts. You can roll this one together. You can wrap it. You can combine it. You can combine those proofs. So like first you can batch transactions and make proofs of multiple transactions. Those proofs are succinct. They are extremely small. And the whole idea about like verifying those proofs is that like it's very cheap to verify the proofs, while it might not be so kind of cheap to generate the proofs. But on the other hand, this can be done off-chain. This can be done like in using powerful machines and so on. So this is something that is not that much part of the equation, as is like verification of the proof. So this is where really why the proofs need to be extremely small and easy to verify. In other words, also like cheap to verify. So not only like batching transactions in proofs and making those proofs smaller, but also combining those proofs and giving versatility that you're not only doing transactions, you can do virtually anything. And on one hand, Ethereum is a great platform compared to like Bitcoin, because it has its own like virtual machine where you can do anything. I mean, it's like a Turing complete machine, and you can program anything into it. So it's not just for like writing down transactions in blocks. I mean, you can do any kind of computation. You can do any kind of distributed computing. You can store data. You can do any kind of or proofs about like owning the data. It can have like enormous amount of applications. And the important point in all this is to make eventually those proofs succinct and small by combining them, and by having also proofs coming from many different sources being able to be combined in kind of an efficient manner. And this is the point probably where we kind of touch up on proving markets and so on, because it's at this moment there are a lot of what we call layer 2 L2 chains, so that are bridged to like Ethereum layer 1 chain, but they make their own transactions, smart contracts, and so on in a cheaper fashion. But of course, they need to interact. They need to bridge to the main chain, and they need interoperability. They need to operate with other chains, and there are like specifics of each one of those, and it's coming, like the need is coming to have a technology that can accept proofs from multiple chains, that can combine them, that can write them in the layer 1 chain in Ethereum, and also that can include so that it's not anymore like on each chain whoever is kind of owning the chain owns everything that is going on there, but kind of making a democratization where you're able to kind of compete in a market manner, so that whoever takes the role of proof generation, of proof verification, can compete with other players, and whoever kind of has the best ratio in terms of performance, cost, and so on, wins on this market. And one model, of course, is that kind of creates this fair, or there is a potential. This technology is yet to come, so we are working actively on development of this. Is basically to kind of have a sort of proving markets where eventually there will be like an auctioning system where you're going to have basically different kind of provers, different kind of verifiers that based on their performance, of their usage of resources, of the cost, and so on, are going to have like a fair price, and then people will be able to choose like in an automated system which one to use, and all the players, all the stakeholders will be able to benefit in kind of a fairly manner. And the beauty, of course, is that this should be like a fully automated system without any kind of possibility of third-party intervention or kind of skewing the system and so on. So this is my kind of vision of how this thing should look like in the near future.
Yeah. So that's really interesting, and Slobodan and I have talked a lot about the proving markets, and I'm going to throw you a little bit of a curveball here. I'm very curious what you think. So obviously, with Ethereum, in the initial early days, we sort of had gas, and this is sort of you sort of use ETH to pay for the computational steps and storage operations that would sort of happen whenever you submit a transaction. And that's sort of kind of simple to understand. But of course, along the way, much more complexity has emerged. The network has transitioned, and now there's sort of like staking, and there's validators, and there's all sorts of different, there's slash conditions, etc. So when we talk about the proving markets, we've got schedulers, we've got sequencers, we've got multiple actors in this, let's say, fairly complex system, where, the potential for more complexity and therefore things to go wrong, or maybe in just an open, free market context for actors to find exploits and somehow manipulate the system for their benefit. Obviously, we see that with MEV and Ethereum, etc. So I'm just wondering if you can talk a bit about the complexity of the proving markets and some of the ways you imagine things can go wrong I'd be very curious to hear.
Yeah, complexity is already very high and it's growing every day, which on one hand can be discouraging. We had a lot, like as you mentioned in the past, even in kind of less complex setting, we had a lot of potential kind of exploits, mishaps happening that kind of destroyed confidence of people in general, like in blockchain technologies, and had bad reputation. And it's kind of really important to try not to repeat those mistakes. On one hand, on the other hand, like there are certain good practices, and in many cases, those were not like when these things were happening. Those were not really their mistakes, but they were either omissions or basically bad exploits when like the people who the actors who should have been like really beyond a doubt and like not malicious in any way, acted as kind of internal actors acted maliciously. This is one thing we should be or we have to think of preventing. Another thing is, of course, making a fair system, and there I particularly think of about scheduler and about like proof aggregation, where the system should be able to regulate itself and kind of defend itself from malicious actors and people who are trying, or let's say entities that are trying to destroy it or overtake it or exploit. And this is it's not very easy. What we are trying to kind of build and a little bit like a preview, a technological preview, we are trying to build a system that particularly involved with respect to like a proof aggregation, but also like scheduling that will not discard or, well, first it will not have any preposition or about maliciousness or fairness or like right or wrong. So at the beginning, every kind of submitter of proofs will be taken as equal in a sense. And the idea behind the system is that if you're a malicious actor, you're going to try, of course, getting your false proofs submitted to the chain eventually, but the system should be made in a way, and this is what we are trying to do, that this becomes very, very costly for you on one hand, so for the malicious actor, and there is no really cost advantage in the end, so that the system regulates itself by kind of adjusting the costs of proofs being submitted, being verified, and so on, in a fair sense, so that a malicious actors would not have like could not or be disincentivized financially in terms of again proof costs or verification costs, to like try to bring the system down or exploit the system. And I mean, this is again this is just touching the surface, but the idea is to have like a smart system that is determining the prices of proofs on the fly, and making it kind of resistant in a sense that all the players, for example, that are stakeholders that are running, for example, the proofs, generating the proofs, would still get a fair payment, even if some malicious like actor tries to push like a fake proof through the system. So they wouldn't suffer in this. And then in addition to this, in the end, we're looking into kind of fair redistribution of whatever is left after those stakeholders get their share back in the pool. And that's now going even more technical into this. The important point there really is to understand very well the system before we even build it. So during architecturing and designing the system, we are looking very much to validate it on very complex simulations. We are trying to build more and more complex models and to validate this. And this is where it kind of touches also the expertise from other fields, for example, from the fields of energy distribution, calculating the cost, like energy market prices and so on. I mean, even though it's on one hand, it might look as totally unrelated, there are a lot of technological similarities and where we can kind of benefit from multidisciplinary approach and from taking the good practices from different fields. So,
yeah, Alberto often jokes. No, it's very good explanation. I mean, Alberto often jokes that it's basically like you turn it into a business model, essentially. When you don't have a presupposition of what's right or wrong necessarily, but it does kind of raise. It's interesting to talk about this because it does sort of highlight that, in fact, as these proving markets emerge, complexity will just sort of also seemingly grow, and ultimately free market dynamics are going to figure things out. But there's definitely lots and lots of research that goes into this, and I'm just wondering, before we get into signal processing, I'm just wondering if you could talk a bit more about, given where we are now, if, as you said earlier, there has historically been this trend towards ASICs, for example, in the case of Bitcoin mining, if we end up moving in that direction with ZK proving, I would argue there's going to be an FPGA interim step. But how does introducing, if you can imagine, ASICs, ZK proving ASICs into the equation, sort of add or potentially kind of reduce some of the complexity?
Yeah. So one thing that is kind of a bit of pre-request for this is also some way of kind of standardization, and a lot of complexity comes from the fact that there is not that there is no standard, but that there are so many different variants and flavors of ZK proofs, of ZK-based systems, all possible combinations, and it's a developing, constantly developing technology. It's probably one of the fastest developing technologies too. I mean, I can see this, like how much we kind of moved and used, how many new stuff came in just last 3-4 years, and there was a lot of let's say mathematical background that was developed 20-30 years ago that nobody found application till recently, and now people absorbed all this kind of pre-knowledge and are developing more and more and getting more and more knowledge into this. However, coming back to the complexity and how to resolve this, well, with kind of free markets, it's not only that the most, let's say, the most efficient technology is going to win on one hand, but also it's gonna or basically it's gonna stimulate. So it's kind of a natural filter where you have a lot of proving systems that are being aggregated and combined together at one point, naturally by the market economy, the more efficient ones will get the higher payoff. So the less efficient ones will be filtered out. And with this, we'll get more kind of clarity in what specifically, like what kind of cryptographic primitives and specific prover types, verifier types, and so on are the most efficient. And this is the point where it will be good to jump, make this leap, and go with dedicated ASIC technology. I have to mention that at the moment there is a lot of development in this direction, and you rightly pointed out, FPGAs are some kind of intermediate step. For the audience that is not so much into this, they are really something in between, combining best of two worlds. On one hand, like you have GPU accelerators that are almost as easily programmable as general purpose CPUs on one hand. On the other hand, really doing low-level optimizations and building things in hardware unlocks a great potential, like orders of magnitudes, on top of like what's, for example, GPUs as accelerators can offer, and they can already offer a lot compared to like what general purpose CPUs bring. The nice thing about like FPGA accelerators is that you can reprogram them, and you can kind of have this much shorter development cycle, where we are not talking about a year and a half till like you get chip on the market from the point where you start developing, and that's assuming if you're like a really major company with a lot of experience in ASIC, in building ASICs. You can substantially shorten this cycle, get it to like couple of months. Of course, it's never going to be as efficient as like programming a GPU, but it offers this kind of intermediate step. And at the moment, there are some players also on the market that already offer some ASICs. And I have to say, in certain, for certain fields, for certain type of provers, they can be very efficient, and they can be like a solution, or in some way like help accelerate not only like the proofs or kind of the market, but also accelerate technology development. Because a lot of stuff will also from the let's say mathematical concepts, from the communication concepts and so on, will start getting adjusted and optimized for future acceleration, for implementation in the ASICs and so on. And really, in the end, to get like all the performance from the table, you would really have to dive into and really make a proper ASIC. So something that is not like a programmable, in a sense like FPGAs or GPUs are, but it is really tailored for the specific application, specific type of a prover, specific field, and so on. And then comes another point, and this is really important point of ASICs, and this is the cost. And while you can kind of make a lot of acceleration with like dedicated accelerators, you can gain a lot of performance. They're still quite costly, and the eventual goal is to get the cost of like those ASICs to be what's basically cheap cards, graphic cards, or like very cheap CPUs today's are, and then everyone can get access, can get hold of this, and in a sense you can also incentivize people to start like using them and contributing and becoming stakeholders and so on. And in that way, that's kind of the real road to getting like distributed proving, because at the moment we don't have this. I mean, this is still mainly done off chain mainly done by a single entity and so on. But in order to be really able to democratize this and make it available to everyone, you need to have like a relatively cheap ASIC or give access to this to everyone. And I think that's the ultimate goal. And many people really kind of dream about this. And I have to say it might look as kind of a distant dream, just maybe a year or two ago, but it's like looking more and more as a reality, and we are very, very close to this, like a couple of years in the worst case. I mean, we'll be there.
Yeah. Yeah, and it's interesting, and I totally agree, by the way. So obviously incentives have to propagate. I mean, of course, people mined Ethereum and bought hardware in order to do that because they wanted to earn Ether. Likewise with Bitcoin. With these coming proving markets, it's a multifaceted, multi-tiered marketplace wherein, first of all, on the demand side, there has to be demand for proofs. And so you can already look to some applications. For example, IPFS has huge demand for proving even right now. But also in terms of consumer applications, some of the stuff we're focused on at Telos, for example, user-generated proofs. And recently we demonstrated, for example, generating proofs on a mobile device using RISC-0. And so the extent to which you can kind of create this very low cost, very fast Web 2-like experience that's almost like using Apple Face ID to generate a proof that you have a valid license when you go to rent a car. That's the classic example we give. And so we think users will find that much more attractive, and businesses as well, rather than sort of like now you have to hand over your identity or worse, put it on chain. And so from a self-sovereign identity perspective, we have very strong reasons to believe there's going to be tremendous demand for realizing something like self-sovereign identity, both for people and machines as well. So I guess just switching gears here a little bit, we have just a bit more time. You talk about signal processing quite a bit, and I'm just wondering if you can kind of dive into that a little more, just so kind of our community can get a sense of what you're talking about, what it means, and why it's important.
Okay, I'll touch upon a little bit on this. This is more like into technology and kind of development of technology. So from let's say a short introduction from standpoint of provers, from those succinct ZK based, so zero technology based provers, since we also have like optimistic rollups and so on, but particularly with the zero technology, which I feel strongly will be like taking dominance slightly. And it will be the winning technology. We have two types of this kind of proofs, like snarks and starks, which differ in a sense of how you set up the system in the first place. Whether there is some kind of you have to have certain kind of ceremony, you have to have certain setup done before you can start, or you can start from a ground zero. And Starks, they really offer this kind of possibility that you avoid this kind of a loophole of starting the whole system, because you don't have to generate any kind of keys. You don't have to have like anything that might become like a security issue, that might become leak, that might enter like the malicious actors that can kind of generate coins out of nowhere and so on. So that's kind of one advantage of this kind of proof-based systems. Today we see a lot of hybrids, so like it's very hard to kind of distinguish where the kind of where one kind of type of system blends into another and so on. But there is one thing which is kind of interested there, and this is like the type of the fields. We are talking about like a field arithmetic, where we have like the prime-based fields, and all the computation is done in those prime-based fields. There are a lot of cryptographic primitives that we rely upon to build those systems. And mainly those Stark systems, they depend a lot on hashing of so-called Merkle tree type based commitments, where you're hashing your internal polynomials, and basically those committed trees, those hash trees become your kind of commitments in the prover system. And we see a trend there, and this trend is to use smaller and smaller fields. And one interesting thing is, for example, we are still using those prime fields, which are not very much. So they rely heavily on multiplication and addition, which are, as we know, costly operations, especially if you have to do a really huge amount of them. And recent years, we have a lot of developments, particularly with GPUs that enable this, because GPUs inherently do a lot of multiplication and addition, like fuse, multiply, add operation is kind of the cornerstone of it. And this is why also GPUs kind of were very helpful there. But it only works if the field size is relatively small. And that's where kind of this Stark-based provers with a smaller field size kind of bring benefit. And there is another potential new alley to explore, and this has already been started using so-called binary tower fields. And why they are so much better in terms of proof generation and then connecting to ASICs, because they can be very fast executed in a kind of custom developed hardware, because they relied on basic gate operations like ANDs and ORs, XORs, and not so much on multiplication and addition, which are more costly operations. And there comes the link, because a lot of these kind of application of those binary tower fields is from the field of signal processing, from error correction codes and so on, and a lot of on one hand mathematics, underlying mathematics, but also a lot of potential hardware optimizations for the acceleration has already been developed, because error correction, encoding, encryption, and so on. Most people see, for example, or people know that blockchain and crypto technologies are based on heavily relying on cryptography. But there is a slight twist or difference between classical cryptography that is used for encryption and decryption, either asymmetric or asymmetric cryptography. They all rely on typically binary fields, not prime fields, and bringing this part of the technology into ZK. This is what I see as kind of a potential avenue that will bring a lot of speed up, cut the cost down, and that will really bring the life to ASIC. So that's kind of the link, very subtle, but the link from signal processing, from error correction codes and so on, all the way to zero knowledge. And another a good example is that underlying technology also in this Stark based proofs is really very similar to error correction codes, because they rely on this extension of Reed-Solomon based codes, which are error correction codes, where you have a group of allowed codes, and then all possible group of codes that includes all possible errors. And this is how basically error correction works. So you have your main codes and all possible extension of those codes that includes error in transmission, communication, and so on. And the twist to this, or application to this in zero knowledge, is that instead of compensated for the error space, you increase a lot the basic space of codes, so that the total space becomes much larger. And this is how you do the zero knowledge transformation. So you have like codes which contain your initial information, and then you expand them in the bunch of codes which are mathematically, of course, related. They're part of the same group, of the same field, and so on, as the basic codes. But they are essentially, because the codes are like a polynomial representation, so they're just a representation of polynomials that contain original information. But then when you extend them, suddenly those extended codes, they don't contain any more like the initial information. So this is where the kind of the knowledge gets lost. You retain still the proof of having the knowledge, but you kind of in a very elegant way create zero knowledge. So basically remove the knowledge, any perception of knowledge from the proof itself. And this is another interesting link where like the signal processing found its application in one of the fundamental zero knowledge technologies in Stark proofs.
Yeah, wonderful. It sounds like it's almost the inverse of reducing a solution space and then brute forcing if you're trying to, for example, crack a key.
Yeah. True.
Yeah. Super cool. Well, I want to thank you very much. This has been a wonderful conversation. We should definitely do this again. I also just want to say one thing about Ponos Technology. You talked about standardization. You guys are doing great benchmarking right now, and I think the world should pay very close attention, because I think Ponos is going to emerge with basically a set of benchmark standards. You guys are doing tremendous research. Let's definitely please do this again very soon. Signal processing, error correction. This is what everyone should be thinking about, and I hope we can stimulate a lot more conversation around some of these topics. So thank you very much. Super cool. And
thanks a lot, John. Related, just one last word related to this, what you mentioned. We think that benchmarking really is kind of important. Standardization is important because we see a lot of like new technologies or type of provers and so on getting in, but we don't see clear kind of demonstration of performance. So a lot of claims, but it's kind of a wild west. And in order to have like a system where you're going to have a market, you need to have kind of standardization. And the very important point is to be able to fairly and accurately benchmark the performance, cost, and so on of various systems to be able to design like a fair market, or basically arbitration system that will enforce or create this fair market.
Yeah.
So
absolutely.
Thanks again for the opportunity. And
no. And let's talk again soon, and maybe we can focus a little bit more on benchmarking. I think it'd be very valuable.